All right, let's do our usual sound check. I can hear myself, and do I see the video footage coming in? Do I see my hand moving in front of the screen? That also looks like a yes. Okay. I'll put away the headphones and we'll get started. Did I remember to mute it there? Yes, I did. Okay, perfect. Sorry, I'm a bit late, but better late than never, I suppose. So, what are we going to do today? Let's see. I mean, I have a general idea, but the day has been quite eventful for me, so I might need a bit of time to gather my bearings here and figure out what it is that I want to do. So last time we ended off with elevator problems, and I choose to start with elevator problems when I do the force unit, force chapter, whatever you want to call it, because it keeps things one-dimensional. You don't have to worry about the vectors in the other dimension. I guess we could have also done horizontal problems, but horizontal problems would still involve vertical forces, and people would end up wondering what effect that would have. So I figured that if you're going to have forces in the vertical anyway, you might as well restrict it to purely vertical so that you don't have to trouble students with those thoughts just yet. So yeah, and I think I left some of that as homework, if I remember correctly. I don't know if I really need to go over much of it because I already did do that. If you go to the, let's switch screens for a minute here. If you go to the course plan, which is linked in the description, always linked in the description unless I forgot to copy it over somehow. If you go to Unit 3, Force, and scroll down to the practice section, it was the one-dimensional force problems PDF. For a lot of these, I have already unlisted solutions videos. The only way you can get to those videos is if you have the link, and I haven't posted them publicly anywhere except here, so yeah, that should be your only way of getting to them. Either that, or you're one of my students and I sent you the link before you had ever even seen this, but yeah, those are the only two scenarios. So yeah, solutions are already available. I might still go over some of them in these streams. I might still go over the solutions to some of these problems, and I think I might actually want to do maybe not the one from last time, but the next one. More vertical force problems and intro 2D problems. So let me see, do I actually have that open? This was the one from last time. And then, yeah, this should be the next one. Okay, yeah, I think this is a good place for us to start, and maybe that will give me time to sort of figure out what I want to do today. I do have some idea of it, so what I want to do, obviously, is transition to 2D force problems. We're going to have some horizontal problems. I think this one actually, yeah, this one ends with a horizontal problem, so we'll get to introduce the topic of friction. And apart from introducing friction, we might do tension problems with multiple connected objects. I'm still not entirely sure if that's something I want to do today or next time, but we'll figure it out as we go. And what else? What else? I want to talk about the friction force. I think I will... Actually, no, we'll do friction and then we'll do... Let me see, what's the next one? We'll do friction. I think I want to talk about Newton's third law, and yeah, we'll do this. We'll do tension with multiple connected objects. Yeah, I think that'll be the core of what we want to do for today. So without further ado, let's get started on this. So this shouldn't be too hard for you if you already did the recommended practice that I gave at the end of last stream. So it basically just combines what used to be 2 problems in the previous document and just has you do it all in one go this time, all in one problem. So it says an elevator with a block sitting on its floor is supported by a cable as shown. If the elevator itself has a mass of 600 kilograms, find the tension in the cable when... Actually, I think I'm going to skip number 1 because we already did the normal force version of it last time. Let's do number 2, the one with tension, because they're both going to be virtually the same problem. And yeah, for G, I'm going to use 10 meters per second squared this time, just so that we can go through the calculations a bit quicker. So let me switch back to my document camera, and let's begin. Oh, and I need to make sure that is visible. Definitely don't want to screw that up. I don't know why my split screen isn't exactly even, but that's a concern for me. You guys can't see that. I have my streaming screen and my streaming software both on like 2 halves of the same screen, and I don't know, there's something about it that just doesn't feel right, but I'll deal with that. Anyway, so it said, an elevator with a block hanging... Actually, let me switch back. It says, an elevator with a block hanging from its ceiling by a rope is supported by a cable as shown. If the elevator itself has a mass of 300 kilograms, find the tension in the cable when A, the elevator is stationary, B, it accelerates upward at a rate of 8 meters per second squared, C, it moves down at a constant speed of 4 meters per second, and D, the elevator accelerates downward at a rate of 5 meters per second squared. So we have 2 objects here. We've got the block and we've got the elevator. We've got 2 objects, one of them being the block and one of them being the elevator. So I'll draw just a copy of the original diagram first that was given in the problem. So we've got a rope here, and then we've got some sort of elevator cable here. And then what I'm going to do is I'm going to draw the 2 objects separately. I'm going to draw the elevator, which it said was 300 kilograms. Yeah, 300 kilogram elevator. And the block, I can get away with it this time. I shouldn't have drawn this separation too close, because if there were horizontal forces on this thing, it would be in the way of my diagram. But fortunately this time it's all vertical, so I can get away with it. And the block was 40 kilograms. So, rule of thumb, when you're dealing with multiple objects require multiple diagrams. As long as you remember that, you are good to go. So what forces are acting on each of the objects? I'm going to start with the block. So the block is connected to a rope, so there must be a force of tension acting on it, and that force of tension must be directed upward. I'm not drawing to scale because the force of tension will sometimes be greater and sometimes be smaller as we move through different parts of the problem. Downward, there's, of course, a force of gravity acting on the block. I guess we can call it force of gravity block to distinguish it from the force of gravity that will be on the elevator itself. So we move on to the diagram of the elevator, force of gravity. I'll just say LEV for short. I don't know if you guys can hear that distant knocking sound, but that is a sound I've been hearing for the past couple days, That is a bird, specifically a red cardinal, that has gotten into the habit of pecking at my kitchen window. I've tried to get it on camera, but every time I get close enough for the camera to actually, see it clearly, it flies away. Anyway, where were we? So, force of gravity on the elevator is there. We have a force of tension from the cable pulling up on the elevator, so that's force of tension cable. But there's also the force of tension of the rope. The elevator is connected by its ceiling to the block via a rope. There's a rope connected to the ceiling of the elevator, and it pulls down on the ceiling. I would just call both of these force of tension rope, but I think just force of tension without a subscript is enough to tell us that this is the force of tension associated with the same rope. And we've already called this one cable, so there shouldn't be any confusion anymore. We can tell that this tension is different from this tension. These two are from the rope, that one's from the cable. And with that, our diagram is complete. There shouldn't be any friction forces here, and there's no springs involved, and there was no mention of an applied force. I guess you could technically, if you wanted to avoid having to call these tensions different names, you could call the tension in the cable an applied force. That's one way around it if you don't like, writing out whole words as subscripts for your variable names. That's one option that you have. But otherwise, our diagrams are complete. So now we move on to questions. They were asking, let's see, what's the tension in the cable when the elevator is stationary? What is the tension in the cable when the elevator is stationary? That's part A. Actually, I think I can write my answers up here. So part A, when the elevator is stationary. Well, if the elevator is stationary, then, and it's not speeding up or slowing down, then we know that the acceleration is 0. And that applies to both the block and the elevator. So net force block equals 0, and also net force on the elevator is equal to 0. And net force on the block is just going to be forces up minus forces down, or you can do down minus up. You could define down as the positive direction if you wanted to, but most people are going to use up as positive unless there's a good reason to deviate from that. So that's what I'm going to go with for now. There will be times, we will see soon enough, if not towards the end today, maybe next time, we will see situations where it makes sense to use down as a positive. But anyway, this is going to be forces up minus forces down, so that's going to be force of tension in the rope minus force of gravity on the block. That would be the mass of the block, which is 40 kilograms, times g, which I'm just going to substitute as 10 for this problem. Okay, and then net force on the elevator is equal to the mass of the elevator times its acceleration. 0 is equal to forces acting up on it, so that would be the force of tension in the cable, which we need to find out, minus forces down. We've got the force of tension in the rope, and also minus the weight of the elevator. Force of gravity would be 300 times g, so minus 300 times 10. Yeah, I didn't make enough room for this, did I? Okay, so if you did the previous problem set, then you learned that first you have to figure out what the tension force is on the block, and then from there you can plug that into the rope tension force on the elevator, and that will leave you with just one unknown, being the tension force in the cable, and the rest is algebra. But we can go a step further than that. We can actually go a step further than that. So I'm going to rewrite these equations again, but this time in a more general form. This time I want to do it just in a more general form. Net force on the block in general is the mass of the block times the acceleration of the block equals the rope tension minus the mass of the block times g. And net force on the elevator equals mass of the elevator, I'll just abbreviate it, times the acceleration of the elevator is equal to tension force in the cable minus the tension force in the rope minus the mass of the elevator times g. So I did not call these acceleration block and acceleration elevator because I know, just through common sense, that however this elevator moves, the block is going to move in line with it, in pace with it. Neither one of them is going to move past the other. At least that's what common sense would suggest. That's easy to see if you picture the elevator going up. If you picture the elevator going up, then there's no reason for the rope connecting the elevator and block to loosen. But on its way down, I guess technically if it goes down too fast, you could have a scenario where the elevator accelerates down faster than the block does, and then the rope kind of just slackens temporarily. Let me get some sort of rope-like object to illustrate what I'm saying. We'll take this lanyard, for example. So the idea is that if the elevator goes down faster than the block does, then you see the rope kind of loosen a little bit like this. Maybe just grab one section of it. So instead of it always being taut, it might slacken a bit. But we're going to assume that that doesn't happen. And that's the natural assumption to make unless there's something in the problem to suggest otherwise. That's what you should assume. Just do a little bit of psychology and assume a certain intent from the problem writer. Anyway, so when we write it out like this, if these accelerations are the same, then what I can do is I can combine these two equations together. I can just add these two equations to each other. And what happens then is you get mass of block times A plus mass of elevator times A. I can factor out the acceleration. Mass of block times acceleration plus mass of elevator times acceleration can just be rewritten like this, is equal to, let's see, force of tension minus M block G, force of tension cable minus force of tension. So these two tension forces are going to cancel out. Right, you've got force of tension in the rope and minus force of tension in the rope. So those will cancel out, and you'll just be left with force of tension in the cable minus the weight of the block and minus the weight of the elevator. So minus M block times G and minus M elevator times G. And actually I could, well, I'll write it out as two separate terms for now, and I'll rewrite it one more time underneath. So I can do M block plus M elevator all times A equals force of tension in the cable minus, and then if I factor out the G, if I factor out the minus G rather, then this becomes mass of block plus mass of elevator all times G. So this is a bit of a shortcut you can take. You don't actually need it here, but it is a shortcut you can take, and we will see problems where I wouldn't say you need to, but it helps. Well, actually, let me think. Actually, you might need to do it in some of the future problems that I'm thinking of, unless you are willing to deal with a certain headache. But yeah, we don't have to do it this way for this problem, but this is an option. And what does this actually tell us? What does this actually tell us? So this tells us that if you combine the mass of the block and elevator, if you treat them as a single object whose mass is 340 kilograms, if you treat this as a 340 kilogram thing, if you treat it as some sort of 340 kilogram thing, then all the internal forces disappear. That is, the forces, in this case, I guess just the tension forces between the block and elevator ceiling through the rope would disappear, and all you're left with is the combination of the weights, which can now just be represented as force of gravity on both block and elevator, block plus elevator, equals 340G, and the cable tension. And that's exactly what this equation tells us, right? If this was your diagram, this is what your equation would be. If you had a 340 kilogram object, you would do 340 times the acceleration equals the force up minus the force down is 340G. So yeah, if this is feeling like you're drinking out of a fire hydrant, don't worry about it. I'm just kind of introducing the idea right now so that it'll digest more easily when we present the idea again later. But for now, let's go back to doing things the traditional way. So I can go back here and solve for the force of tension. 40 times 10 is 400. If I add 400 over to the 0 side of this equation, then I get 400 equals the force of tension in the rope. 400 newtons to be specific. Gotta remember the units or else you won't get credit. Okay, we can substitute that 400 newtons in here because whatever tension the rope exerts upward on the block, an equal amount of tension is exerted downward on the elevator. This is just a basic understanding of Newton's third law. I know we haven't really discussed Newton's third law yet, but I hope you find that convincing for now. And we'll talk about Newton's third law in more depth later today or next time, depending on how things go. Actually, we'd have to do it today. Yeah, I think we would have to do it today, but we'll see. Anyway, we still have over here 0 is equal to the tension in the cable. Minus the force of tension, which we now know is 400 in the rope, minus 3,000 for the weight of the elevator, and we get minus 3,400. If we add 3,400 to both sides, that's 3,400 newtons for the tension in the cable. And this is what I should have actually circled as my answer. You know me, if you've seen my other streams, I also tend to circle and box things that are important steps on the path to the solution and not just the solution itself. Okay, so that takes care of part A, what happens when the elevator is stationary. Part B says what happens when, or what's the tension in the cable when the elevator accelerates upward at a rate of 8 meters per second squared. What happens if the elevator accelerates upward at a rate of 8 meters per second squared? Okay, so defining up as the positive direction, I'm actually going to do it down here. So for part B, if the acceleration is 8 meters per second squared upward, then I'm going to do mass times positive 8. So for the block, it's going to be 40 kilograms times positive 8 is equal to force of tension minus times 10 again. That part stays the same. I should have probably just written it as 400 outright. And then for the elevator itself, we can do cable tension, or no, getting ahead of myself, 300 times the acceleration. Net force elevator equals MA, but also equals the sum of the forces. That's the cable tension minus the rope tension minus the weight of the elevator, 300 times 10, or 3,000. Okay, 40 times 8 is 320, and then add 400 to both sides. 320 plus 400 would be 720, so force of tension equals 720 newtons. And then if I plug that in here, then I've got minus 720 and minus 3,000 is minus 3,720. And over here we'd have 2,400, so 2,400 plus 3,720. That would be 6,120 if I'm not mistaken. 3,700 plus, or no, 3,720 plus 2,400. Yep, 6,120. Okay, so force of tension in the cable is going to be 6,120 newtons. Okay, part C says, what happens if the elevator moves downward at a constant speed of 4 meters per second? If you paid attention at the end of last week's stream, you remember what the trick is here. It said constant speed, and it also tells us that the direction is downward, so both magnitude and direction are constant. Constant velocity means the acceleration is 0. So the answers to part C are the exact same as they were for part A. As long as the acceleration is 0, it doesn't matter what the velocity is. It can be 0, it can be 100, it can be 5, it can be whatever. Force is not about velocity, it's about acceleration. Let me go ahead and switch to another color. I guess I haven't really used orange today. So yeah, part C, same as A. Part C, same as part A. So we can skip on that work. We've already done it. Well, you wouldn't say this on a test. What you would do on a test is you would copy down 3,400 newtons as shown in the solution to part A, or something to that effect. And then part D. Part D says the elevator accelerates downward at a rate of 5 meters per second squared. So that's going to be an acceleration of -5. So just writing these net force equations again. Net force on the block equals the mass of the block times the acceleration. So 40 times, this time the acceleration is -5, equals the sum of the forces. Force of tension minus the weight of the block is 400. So tension in the rope minus 400. And then for the elevator itself, we've got 300 kilograms times an acceleration of -5 equals the tension in the cable minus the tension in the rope, and also minus the weight of the elevator, 300 times 10, or 3,000. Okay, so force of tension in the rope, we've got 40 times -5 is -200. Add 400 to both sides, and you get +200. So you get force of tension in the rope is 200 newtons. And then if we plug that in over here, we'd get -200 and -3,000 is -3,200. And here you've got -1,500. If I add 3,200 to -1,500, that's going to be 1,700. Force of tension in the cable must be 1,700 newtons. And there we go. That takes care of problem 2 from that set. Now then, the next problem requires us to introduce the concept of friction. We need to go over how friction is calculated. So it says a worker pushes a box along a rough floor as shown. The worker applies a force of 400 newtons to the box, and the box accelerates to the right at a rate of 3 meters per second squared. Calculate the following: the normal force on the box and the force of friction on the box. And then the bonus says calculate the coefficient of friction. So we can actually do part B without knowing anything about friction just yet. And then for the bonus that talks about coefficient of friction, that's when we'll have to pause and look at the topic of friction more closely. But yeah, let's do parts A and B of this. So part A, well, let me copy the diagram first. So we have a block. I'm not going to bother drawing the person because they'll just be in the way. But we've got a block which is 80 kilograms in mass, according to the diagram. And let me actually remember to, move back to my document camera. I knew I was forgetting something. Definitely don't want to screw up like I did last time. I think I made that mistake twice. The second time was less of a problem. I was trying to show off something that I did end up successfully showing off in a subsequent stream. So that wasn't such a big deal, but the first time I caught myself forgetting to put on my document camera last week. Oh boy, that was something. Anyway, so we've got an 80 kilogram block being pushed to the right, so I guess I'll go ahead and actually draw my diagram here. There's going to be a force applied to the right, which is actually a normal force if you think about it. A person physically pushing on a box is just creating a normal force between their hand and the box perpendicular to their hand. So their hand is going to be vertical and the normal force is going to be perpendicular to that, so horizontal. But we'll call it an applied force for convenience's sake. And let's see, they actually told us the worker applies a force of 400 newtons. So I'll go ahead and note that on my diagram, 400 newtons. We know this box must be on a planet, presumably Earth. We have no reason to assume otherwise. So there's going to be a force of gravity, mg, and I'm still going to use 10 here. So 80 times 10 for g gives us 800 newtons. There must be a normal force acting upward on it. And I had these tick marks on my diagram telling me that the floor is rough, and also the problem explicitly mentions friction, so you know there's a friction force. They said it accelerates to the right at 3 meters per second squared, and assuming that the box started at rest, that would also mean that it's moving to the right. So the force of friction is a kinetic friction force, and it must be opposite to the direction of motion, so it must be to the left. Force of friction, kinetic, is going to be pointing to the left like that. Okay, so what's the difference between a one-dimensional problem and a two-dimensional problem? Well, usually with two-dimensional force problems, the strategy is to do kind of what we did with projectile motion. Separate the horizontal motion from the vertical motion. You're going to have problems later on where you'll want to separate the force not necessarily into vertical and horizontal, but parallel and perpendicular to the direction of motion. I'm specifically talking about, we will see in more detail later, but ramps. If we have an object going up or down a ramp, instead of right, left, up, and down, our coordinate system of choice will be something more like this. Up and parallel to the ramp versus down and parallel to the ramp, and up perpendicular to the ramp versus down and perpendicular to the ramp will be a much better coordinate system to use there. Although I guess you could still call these X and Y directions, just tilted. But we'll get into that at a later time, probably next week. Anyway, for this problem, we can just use our traditional coordinate system, right and left being the x-axis and up and down being our y-axis, and I will just write two net force equations for my object, net force x and net force y. And I'm going to say my net force x is going to be the mass of my object times the acceleration in the x direction, while my net force y is going to be the mass times the acceleration in the y direction. And I'm going to say right is positive for this problem, so I'm going to have forces to the right, that's force applied, minus forces to the left, that's the force of kinetic friction. And those are my only horizontal forces. For my y direction, I've got forces up would be normal force, minus forces down would be the force of gravity or weight. Now we can rewrite that again, but this time plugging in some numbers. So, in the x direction, we were told that this block is accelerating at 3 meters per second squared to the right. So that would be a positive 3. So mass is 80 kilograms, net force x equals 80 kilograms times positive 3 acceleration in the x direction equals force applied is 400 minus force of friction kinetic. We don't know yet, but we can now easily solve for it because it's the only unknown left in this equation. I guess we might as well do it even though it was part B, no harm in answering that first. So 80 times 3 is 240, and then we've got 400 minus the friction, so I can subtract 240 and add the friction, so I get force of friction, kinetic, is equal to the 400 minus the 240, is equal to 160 newtons of force. Okay, so that is actually part B answered ahead of part A. For part A, net force vertical, what is the acceleration in the vertical direction? The mass is 80 times acceleration in the vertical direction. Well, all they told us was that the box accelerates to the right at 3 meters per second squared. So that must mean that it doesn't accelerate up or down at all, or else they would have mentioned something about it gradually floating up or burrowing down into the ground, even without that, just common sense would suggest that that doesn't happen. In everyday life, you wouldn't expect to push on something horizontally and for it to start accelerating vertically. So the vertical acceleration is reasonably assumed to be 0. And from there, we have normal force upward minus force of gravity is 800 newtons. Add 800 to 0, and you're left with normal force equals 800 newtons. It is scenarios like this that convince people wrongly that normal force is equal to mg. I had my mini rant about that last week, so you can go back to last week's stream to listen to my explanation again, but normal force does not have a formula. It happens to equal mg here today, but there will be scenarios where that's not the case. Normal force equals whatever it needs to equal, and the only way to figure out its value is to actually do your net force equations and see what normal force the situation calls for. Anyway, that takes care of parts A and B. The bonus question is calculate the coefficient of friction. The bonus question is calculate the coefficient of friction, and for that we need to learn what a coefficient of friction even is. So let's go ahead and talk about the topic of friction. So how does friction even work? How does friction even work? Suppose I have a box on a rough floor, let's say a carpet, for example. Now, I mean, it doesn't even have to be a carpet. It can be wood, it can be, ceramic. Even ice is going to have some friction to it. If you want a zero friction environment, go to outer space, because even air itself has a sort of friction, which we call air resistance or drag. But yeah, how does friction work? Let's assume that we're talking exclusively about solid objects. We will neglect things like drag from air or viscous drag from liquids. We will just focus on the friction between solid objects for now. So how does it work? Basically, if you zoom in on the parts of the bottom of this block and the top of this carpet or whatever surface this may be, if you were to zoom in on it, if I were to draw a zoomed in picture of this, here's what it would look like. The bottom of the box isn't perfectly smooth. On a more microscopic level, it's going to have these sort of jagged edges, and the same thing goes for the floor. The floor is also going to be kind of jagged and not perfectly flat. So what happens is the jagged edges of the bottom of the box will sink into and get stuck inside of these sort of crevices, these little valleys within the carpet, and you need a little bit of force to push against them, because what will happen if I zoom in on like a piece of this again, suppose I get something like this. So here's a piece of the bottom of the box, and then I'll do it in a different color for ease of visualization. What color do I want to use? Let's use this blue. It won't be a perfect fit, of course, but you might get something like this, where if I try to push this, I guess, dark red surface to the right, what's going to happen is over here, all of this is going to bump into each other. It's basically like I'm pushing it against a fraction of a wall. And what'll happen is because it's slanted, it will eventually kind of slide up and move, but not without some sort of resistance. It's kind of like hitting a road bump, except on a microscopic level. You're hitting these sort of microscopic road bumps, and those add up, and the end result of that is they slow you down. They slow you down. They generate some sort of total leftward force that slows you down if you're already moving, and eventually brings you to a stop if there's nothing else pushing you, or increases the required force to actually move you if you do have some force that's moving you along. So I have a PhET simulation that illustrates this a little bit more clearly. Let me go ahead and open that up for you right here. And if you want to find this for yourself, just PHET, PhET simulations, just type that into Google. There it is, just type the word PhET simulations, and then go into their simulations page over here, click on physics, and I would a bunch of these are checked by default. I would leave only the motion one checked, and also under compatibility, usually only this first one is checked. I would check the second one too, because the second one will also include some of the older ones that they've had, which I still use. But they're kind of outdated. They were written in Java, and all of their new ones are in HTML5, so their old Java ones, some of them have been updated into a browser-compatible version in ChirpJ. So you want to make sure that box is also checked. If you're looking for something that I ever show off and you're struggling to find it on PhET, probably the reason is because you don't have this box checked. I don't know why they don't just have it checked by default, but now you know. Anyway, you can look around for the friction lab, which is this. I already have it open in another tab. And yeah, here you go. So basically, they have a chemistry textbook here on top of a physics textbook, and they've zoomed in on this thing. And I think there's supposed to be sound in this, which I don't want. Let's keep that muted. But yeah, you've got these little, I guess they're supposed to be atoms, and if you try to rub them along each other, it doesn't show it really well here, but the idea is that when they move against each other, they do have these micro collisions, and you see they're kind of vibrating faster and faster because, as you know, friction generates heat. And yeah, that's the basic idea. They just bump into each other on a microscopic level, and that slows things down. If you slide it left and right without having them touch, you see that it's really easy, but if they are touching, you find that it's harder, and you see that thermometer over there just keeps going up as long as you keep rubbing the two books against each other. Oh, and eventually, of course, if you rub too hard, that happens and a bunch of atoms get shaved off, which is kind of like how sandpaper works, actually, or how a nail file works if you're doing your nails. So yeah, that's just a very quick basic explanation of how friction works. But there are two types of friction. There are two different types of friction. Oh my goodness. Where was I? Right, two types of friction. So we have static friction. And we have kinetic friction. Static friction is when the object and the surface, or two objects if that's how you prefer to think about it, because the surface is technically another object, although it's sometimes easier to think of it as not being an object. Static friction is what happens when there is no relative velocity between the object and the surface. I say no relative velocity because if the object is moving, if I have, for example, you've seen this, I'm sure, people take out their trash bags on the top of their vehicles or something like that. They'll put like a trash bag on the top of their truck because they can't be bothered to walk their trash bags over. That is a very terribly drawn trash bag. I was trying to draw like the drawstring, but whatever. This is an object on top of a truck. And the truck moves, and the trash bag or whatever is put on top of this truck does not slip, even though it's not tied down or anything. Why is that? Well, that is also static friction. So static friction is when there is no relative motion between two objects, between an object and a surface, not necessarily the absence of motion altogether. If you're still not sold on this, consider yourself standing still in your room. Is your velocity truly zero there? Actually, no. It depends on perspective, because you are standing on a planet that is constantly moving around its own center and completes a full rotation around its own axis every 24 hours. When you consider the radius of the Earth, which is about 6.4 million meters, you're going through a circle whose circumference is, 6.4 million times 2 pi. So about 36 million meters in a day. You are moving 36 million meters in a day. You don't feel it because the earth underneath your feet is also moving at that same pace. If you and the floor underneath you are moving at the same rate, then your relative velocity, what you actually perceive, is zero. So yeah, friction, whether static or kinetic, is about relative velocity. Static friction is when the relative velocity between an object and a surface is zero, which means either both not moving or both moving with same velocity at the same time. Kinetic friction is when their relative velocities are different. So either one moving and the other is not moving, or both are moving but at different rates. That would be a case where kinetic friction occurs. So static friction and kinetic friction for the same surface, for the same type of roughness, will differ. Static friction will tend to be higher. Static friction will tend to be higher. Or rather, what I should say is that static friction can go higher. Let me try and explain this. So, static friction, if I'm going to draw yet again a block on a rough surface. So suppose I apply some sort of force on this object and I try to get it to move. You've had experience pushing furniture. What happens if you don't push strongly enough? If you don't push strongly enough, then no motion occurs. There's no acceleration, which means there must be some force over here canceling out your applied force. That is the force of friction static. So the static friction force is kind of like the normal force and the tension force. It has some sort of maximum that it can go to. Force of friction static maximum. And as long as your applied force is somewhere between 0 and this maximum, the static friction force will always just adapt and change to whatever it needs to be to prevent motion, or rather to prevent relative motion. So the static friction force will go as high as it needs to in order to prevent relative motion up until it's maxed out. And whatever this maximum static friction is, whatever this maximum available static friction is, the kinetic friction will definitely be lower than this maximum. Kinetic friction, force of friction kinetic, is mostly constant. Force of friction kinetic is mostly, I put in parentheses, mostly constant. It's constant enough. But if you want to be super technical about it, it's not exactly constant. We can get away, like 99.9% of the time, we can get away with thinking of kinetic friction as being constant. At least in AP physics, I would say it's 100% of the time. Maybe if you do something more advanced in college, maybe you might end up in some sort of engineering course where you have to worry about the technicalities of variable kinetic friction, but for our purposes, we're just going to assume that kinetic friction is constant. So whatever this constant value is for kinetic friction, it's always going to be lower than whatever the maximum static friction is for that same surface. So force friction kinetic is less than or equal to, well, no, just strictly less than force of friction static maximum for the same combination of object and surface, for the same combination of object and surface. I normally think of friction as just having to do with the surface, but it is actually, it does actually depend on both the object itself and the surface, what material they are made of. For example, you would expect different results from pushing, say, a block of wood along a wooden floor versus pushing that same block of wood along, say, I don't know, a ceramic floor versus pushing a block of metal along those same two surfaces. Wood on wood versus metal on wood versus wood on ceramic versus metal on ceramic. You would expect different friction for each of those objects, even if you gave those objects the same mass. You would expect them to encounter different frictions under the same mass and applied force. But we'll go over all that in due time. There actually is a chart. I should have pulled this up ahead of time. I'll have to see if I can find it live. If not, then I guess maybe I'll show it off next time. But there is a chart that I like to show students. I always have to Google it because for some reason I can't think to just bookmark it and save it. But there's like this one engineering website that has a bunch of coefficients of friction, which we haven't even talked about yet, that talks about like the roughness between different combinations of material. I'll see if I can find that later and show it off. But right now I just want to finish my point here. So kinetic friction, the friction that an object encounters when it's already moving relative to a surface, is always going to be less than the maximum static friction that that same object can encounter on the same surface. This you have probably experienced also while pushing around furniture. You apply a force and you start increasing the force and increasing it and increasing it, and the object still won't budge, and then you increase it a lot, and then finally, once you have supplied enough force once you've broken past whatever this static friction maxes out on, all of a sudden you notice, and this happens really quickly, all of a sudden you notice that keeping that piece of furniture moving is actually a lot easier and requires less force. Like, you can push on the object and push on it and push on it until it finally budges, and once it budges, it gets a little bit easier to keep it moving. You notice that happening all of a sudden. That is the switch between your maximum static friction and your kinetic friction. That's what you're feeling. You're feeling a reduction in the force that's being applied to the left. So at some point, this thing maxes out, and then literally a fraction of a second later, you actually have to ease up on the piece of furniture, or else it'll slip away from you, because now you're under a weaker force of friction, a force of kinetic friction. So I have another PhET simulation that illustrates this idea. Let me see where it was. I think it was this one. Let me put it on screen. Pretty sure it was this one. Forces in motion basics. Yeah, here we go. This one. Okay, so for this object, I want to go ahead and turn all this stuff on. And let's see, so it's a 50 kilogram object. I'm going to start applying force to it. Okay, so let me try and do that again. So as I apply more force, notice that the friction force, that's the red arrow to the left, keeps increasing with my applied force. So right now both are 53, increase the applied force to 62, the friction force also increases. 81, 86, 93, 100, 102, 106. Pay close attention to the friction force and notice what happens. Notice how it jumps down to 94. It was at what, 125? And then suddenly it just jumps down to 94. And now you've got more force to the right than to the left. I'm going to try and ease up on this and bring it, let's see if I can precisely get it at 0. Can I? No. Man, would have been nice if I could get it exactly at 0, but okay. 95 to the right, 94 to the left is approximately going to be 0 net force. And you see the speed over there is pretty much constant. It's still increasing because I can't get it quite at 0 force. But yeah, there you go. If you can get the net force on an object to be 0, and you can probably do it more precisely if you put more mass on this thing. Yeah, let's see what happens now. Can I do this with more precision? Oh, very, very close, but not quite. Yeah, I can't. Can I? Oh, I can do this? Okay. Yeah, there we go. Now I can get it to be exactly 0. Okay, now the sum of the forces is 0, and now the speed will just be a constant 3 meters per second until I change something here. Let me see. I lost my train of thought. I've lost what I was originally trying to say here. Think. Okay, so take this guy off and actually just reset everything. Okay, so moving this box, it required like 120 something newtons. Yeah, 127 newtons about, give or take, is what it took to get this thing to start moving. And now it's under just kinetic friction of 94 newtons. I guess that's kind of hard to read with the guy in the way. Significantly less than whatever that maximum static friction was. So clearly we have a difference between the two. You've been experiencing it all your life, and now we're going over the physics of it. Why do you suppose this happens? Why is it that the amount of force it takes to get something to start sliding against a rough surface is greater than the amount of force required to keep it moving? If you think back to what I was saying earlier about that microscopic view of the bottom of the box versus the top of the floor, what do you suppose the reason could be? Well, when the object is sitting still, or at least sitting still relative to the surface, that just means there's more time for these jagged edges to sink in and fit into each other. It just means there's more time for them to settle down. Versus if all of this is already moving, let's say to the right, then what happens is, because it's already moving, it doesn't have quite enough time for all the pieces to kind of, they're going to try and sink downward at an angle like this, but because they're moving, they might actually miss these little bumps and just glide over some of them. Not all of them, it's still going to be a bumpy ride, but if you're moving fast enough, then some of these little speed bumps you're just going to glide past them. You're going to fly over them, essentially. And so you're going to encounter less bumps overall, less, what would you call it? Less resistance from this bottom surface, and therefore you get less friction in total. So yeah, kinetic friction generally weaker than the maximum static friction. Not always weaker than the static friction itself, because that's going to vary with the applied force initially, right? If we go back to over here, when I first applied to 94 newtons, the static friction also went to 94, and when my applied force was less than 94 newtons, my static friction was less than 94. My static friction just matched my applied force, matched whatever it needed to be in order to keep the sum of the forces at zero. And then only after I went past the maximum static friction available did the friction go back down to whatever the kinetic friction was, which in this case is 94. Okay. I feel like I'm about to forget to explain something really important here, so let me slow down and gather my bearings and review what I've said. So we've talked about how relative velocity determines whether you're under static friction or kinetic friction. We have talked about how static friction is very much like normal force and tension force, equals whatever it needs to be to achieve a net force of zero on the object. Or actually, not even a net force of zero. The static friction is going to be whatever it needs to be to keep the relative velocity at zero. So in the case of this moving truck, actually, if this truck is accelerating, if this truck has some sort of acceleration, then the static friction on this trash bag or whatever you put on top of the truck is going to act in such a way that it gives the bag the exact same acceleration, so that whatever the velocity of this truck changes to, the velocity of the trash bag also changes to the same amount, so that the velocities are always the same at the same instances in time. So the relative velocity stays zero. So yeah, force of static friction will equal whatever it needs to be in order to keep an object at the same velocity as the surface that it's in contact with. And if that surface is accelerating, then that object needs to accelerate at the same rate with the same starting velocity so that their relative velocity can remain at zero. And usually that acceleration will be zero because usually we'll be talking about an object on the ground. But again, this sort of scenario does pop up from time to time when you've got an object that's being dragged along by a moving surface underneath it. Or not even necessarily underneath, but underneath is typically what we encounter when it comes to friction situations. We'll talk about vertical friction situations later. Actually, what about this? This is neither vertical nor horizontal. You could have a rough ramp, which we've seen before. We saw that last week. Yeah, you can have friction in some sort of angle that's neither completely vertical or horizontal. And you can also just, hold something against a wall, right? If you push something against a wall, the object just stays up and doesn't fall down. Why is that? That's because of static friction. Force of friction static. That's probably not even readable, but you get what I'm trying to say here. So static friction will try to keep the relative velocity between an object and a surface equal to zero. Up until, of course, it reaches its maximum. Once you max it out, once you're past its maximum value, well, then it's no longer possible to keep the relative velocity at zero, and that's when you immediately switch to kinetic friction. So for a lot of these friction problems, what you might end up having to do is you might have to calculate what the maximum static friction is, and then compare that to what the rest of the forces on the object are doing. And if the total of the remaining forces is greater than what the maximum friction can keep up with, then you forget about static friction entirely and you switch to kinetic friction. If the sum of your remaining forces exceeds the maximum possible static friction, then you just leave static friction, you remove it from your diagram, and you replace it with kinetic friction instead. Once you've established that movement is inevitable, you would use the movement friction, but not the other way around. Do not start with the assumption of kinetic friction and then go back to see if you get static. That's not going to work. That is not going to end well for you. Anything else I need to say before I move on to the concept of the coefficient of friction? I don't think so, but if I forget anything, I will either bring it up next time or bring it up in like a pinned comment or something. But I do feel like I'm leaving something out. I don't know what it is, though. Anyway, coefficients of friction. Coefficients of friction. What is a coefficient of friction? Well, if you remember the term coefficient from your algebra class, a coefficient is just the number in front of your variable, right? Or in chemistry, I guess, a coefficient is the number in front of your chemical formulas. A coefficient is really just a multiplier. It's a number that you multiply by. Coefficients of friction, they have no units. They have no units. Instead, coefficients of friction are a measure of the roughness, a measure of the roughness between two objects, between two objects. For example, I would expect a carpet to be rougher than, say, a ceramic floor, which I expect to be rougher than, say, ice. So the greater the roughness, the higher the coefficient of friction. Carpets will have a higher coefficient of friction compared to the ceramic tiles, which themselves would have a higher coefficient of friction compared to ice. Ice, I would expect to have a very, very low coefficient of friction. Okay, so coefficient of friction covers roughness, and there are two different types of coefficients of friction because, well, there are two different types of friction. We represent the coefficient of friction with the Greek letter mu. So represented with Greek letter mu. It looks like an M and a U combined together. It's kind of like a fancy M combined with the letter U, and if you fuse these together, you get the mu. You start it off as if you're trying to write the letter M, but then you end it as if you're writing the letter U, mu. Spelled M-U. So if you ever see this, then they're just referring to this symbol. Again, just practice it like with the capital sigma symbol. If you practice it a few times, you'll start writing it effortlessly. I know some like to really truncate it and just do this, which I don't know, man. I like having this kind of short tail on it at the end. Plus, it just helps with the whole. Again, it's an M and a U, mu. It kind of helps preserve that sort of M-ness and U-ness all together. But at the end of the day, I guess it's personal preference. Well, personal preference to a point. You still want it to be readable. If the person grading your work can't tell that you're trying to write a mu here, then you probably need to put some more effort into it. It's not that personal. You still need to adhere to some sort of standard of readability. But yeah, coefficients of friction. So that is one of the things that determines how much friction you get. We already talked about whether it's static or kinetic. That will also determine how much friction you get. But the third thing that determines how much friction you get is how strongly the object and the surface are pressed up against one another. If I go back to this scenario that I drew over here, if you push a book against a wall, you know that if you don't push the book against that wall hard enough, then that book is just going to slide down the wall. It's not going to hold up. There won't be enough friction. If you push it hard enough to keep it from slipping and then you start easing up on it, you can find the exact moment where you are no longer applying enough force on it. What's happening is because you apply less force on it, the wall doesn't have to apply as much force on it, which means there's less. What kind of force between the wall and the book? What's the force that exists between two objects that are pressed against each other? That's the normal force. Same thing with an object on the floor. If I go back to, again, this FET simulation, over here I've got 94 newtons of friction on a 50 kilogram crate, but if I put a person on top, if I add some force, if I apply some force downward, now the weight of this person presses the box into the ground harder, and you saw the friction force went up to 244 temporarily. I think that's what it was. If you apply some force downward, you are increasing the amount of friction that is needed, or sorry, not the amount of friction that's needed, the amount of friction that the object encounters. Let me try and increase this. Is that enough to get you moving? Okay. Yeah, there we go. Okay, so now we are under a circumstance where you've got 244 newtons of kinetic friction. I can decrease the friction now by decreasing the normal force. It works both ways. If I remove this guy now, then the box is not pressed against the ground as hard anymore, and you see that the friction force dropped to 94. And I'm going to pause that there. So how hard the object is pressed against the surface is also going to have an effect on how much friction you get. And that's for both the kinetic and the static friction. So at the end of the day, the force of friction, whether static or kinetic, the force of friction is equal to the coefficient of friction times the normal force. The more strongly two things are pressed against one another, the greater the friction between them. You can also experience this firsthand, literally, get it, hand, with your hands. If you just rub your hands against each other while pressing them lightly, you can slide them against each other pretty easily, but if you really press them into each other and then try to slide them against each other, it's much more of a struggle. And you also generate more heat when you successfully slide them past each other. Okay, so this coefficient of friction for an object that starts at rest relative to a surface, this coefficient of friction, and let me switch colors here because it's been a while. Let's do orange. This coefficient of friction, if I were to graph it, so here's going to be the force that I apply, and then here I'm going to graph the coefficient of friction. So when you first apply force, there's no friction, obviously, but then as you increase the amount of force that you're applying, the coefficient of friction will increase. It varies and it kind of zigzags because we don't live in a perfect world. The roughness of these edges, this jaggedness, is kind of random and unpredictable. So you do get this sort of jagged graph that kind of meanders its way up and down until you hit some sort of breaking point where you've reached the maximum static friction, and at that point your coefficient of friction is approximately constant, and it kind of just zigzags a little, but is mostly a horizontal straight line. That's what I was talking about earlier when I said, that the force of kinetic friction is mostly constant. So from here to here, you are looking at coefficients of static friction, what we will usually represent as mu static. Up here, you are looking at, whatever this value is, Oh, actually I drew this graph wrong. I'll make a correction in a minute. Up here is the maximum, the coefficient of maximum static friction. This is where it maxes out. And then what I drew wrong here is when you switch to kinetic friction, forget this. I'm going to scribble this out. When you switch to kinetic friction, you see a dramatic drop and then a mostly horizontal line. And whatever this line is at, that is going to be what we call your coefficient of kinetic friction. Yeah, there we go. I had a feeling I did something wrong there. So yeah, you apply force, you apply more and more and more force, and your coefficient of static friction ramps up and up and up and up and up while this is assuming, of course, that we're talking about an object that's subject to a constant normal force. The static friction increases to counter the applied force up until you reach some maximum value, and then after that, sharp decline in the coefficient of friction because you start to build up speed and glide past some of these bumps. And then after a while, it's pretty smooth sailing, pun intended, where you get a reasonably constant, not exactly constant, but constant enough coefficient of friction from that point onward, until of course the object comes to a stop, and then you're back to this point in the graph and you have to start all over again. You don't really need to know this graph, but just understanding it conceptually will help. So yeah, coefficients of static friction, you just have the coefficient of static friction for whatever the current static friction is, and then you've got some sort of maximum. A lot of times you will see problems where you will only be given the coefficient of the maximum static friction, so you need to be careful. Most problems, I would just assume if they give you a static friction coefficient, I would not fall for this. If they give you mu static and then you calculate the normal force and you multiply by that normal force, just note that what you're calculating here is not the actual static friction, but the maximum that that static friction can reach. So whatever this is, I would just assume that I'm being given the coefficient of maximum static friction, and I should have made more space for that because that's not very readable. And sometimes what they will ask you, actually, if they're asking you to solve for a coefficient of friction, is they will ask you what minimum coefficient of static friction is needed in order to prevent the object from slipping. At which point, yeah, you would calculate how much friction force is needed for your net force to be whatever it needs to be, 0 in the case of a stationary object, and whatever it needs to be in the case of a moving object in order to not slide off the truck or whatever. You calculate that, you sub it in for your static friction. You would assume that that's the point where your static friction is maxed out, because they'd be asking for the minimum static friction coefficient needed, and then divide by the normal force and get your static friction that way. And yeah, whatever that is would be your answer. What was I gonna say? Man, my brain is malfunctioning too much today. Maybe I should have canceled and tried to do this tomorrow instead, but we're in too deep now, so let me see. Let me retrace my steps and figure out if there's anything I forgot. we covered the symbol for the coefficient of friction. We talked about how it's basically a measure of roughness. We talked about how normal force is the other factor that determines friction, because normal force is how strongly an object and a surface are pressed against each other. So this relationship should make intuitive sense from there. Oh, here's what I forgot. Force of friction static. So maximum static friction is equal to the coefficient of maximum static friction times the normal force. But the better way to think about it in general for the problems that you're going to have is just say force of friction static is less than or equal to the coefficient of static friction, which I would just go ahead and assume is going to be the maximum for most problems that they give you. Whether they write the word max in there or not, I would just assume it is, unless I have reason to believe otherwise, and then times normal force. Yeah, this is the safer way to think about it. And we will eventually do problems where we practice this, so don't worry if this is all feeling overwhelming. It'll make more sense as we practice more problems. I plan on spending a lot of time on this chapter because, like I said, I think last week, but definitely the week before, force is, in my opinion, the most important chapter in all of physics. And it deserves more time. We need to get it right. If we can get this right, then even for physics problems that don't involve force at all, you will, at least from this chapter, my goal is for you to at least learn this sort of style of thinking that is applicable to all of physics. That's what I'm ultimately trying to get at. And for that, we need to slow down and make sure we understand everything carefully. Okay, was that all I wanted to say? Can we finally get back to the problem that started this whole detour? Well, one more equation to list. So for kinetic friction, you don't need the inequality. You don't need to indicate a maximum. For kinetic friction, the coefficient is approximately constant. So for force of friction kinetic, you would just say mu kinetic times normal force is equal to the kinetic friction, and you would just treat the kinetic friction as having a constant value. No inequality needed, no changing depending on whatever the remaining forces are doing, none of that. If an object is moving relative to a surface, then you just have a constant friction that is calculated from mu kinetic times whatever the normal force happens to be. I think what I want to do is just relist those on a new page just for clarity, because I know even with all of this color that I'm using, it could easily be a jumbled mess if you're staring at the wrong parts of the page. So one more time, force of friction static is less than or equal to mu static, or mu static max if you want. A lot of times book problems will not give you this max, they'll just call it mu static, and you're supposed to assume it's the maximum, times normal force. And then force of friction kinetic is an equality, mu kinetic times normal force. There we go. Now we can go back to the problem that got us started on this. Let me see what page it was on. Here it was. So The bonus question was calculate the coefficient of friction, and for that I guess I need to go back to where did I even do this? Oh, yeah, it's on this page still. Right, the force of kinetic friction, we calculated it would have to be 160 newtons in order for the acceleration to be 3 to the right for this object. Oh, wait, I forgot to switch screens again. At least this time I caught it sooner rather than later. So over here, we're back to this page. So we had 160 newtons of kinetic friction is what we calculated earlier. And we calculated the normal force is 800 newtons. So then the bonus question is asking what is the coefficient of friction. They didn't specify kinetic or static, but we know it's kinetic because that's the only friction we have. And for that we can just say force of friction kinetic equals coefficient of kinetic friction times normal force. We know that the kinetic friction force is 160 newtons from our calculations earlier. Equals kinetic friction coefficient times 800 newtons of normal force. 160 over 800 is exactly 1/5 or 0.2, so the coefficient of kinetic friction for this surface must be 0.2. And there are no units for this, because if you think about it, this was 160 newtons, we divided by 800 newtons. 160 newtons over 800 newtons, newtons over newtons cancel out. So the coefficient of friction has no units. I know I mentioned it before over here, but now we can see mathematically why that has to be true. Coefficients of friction are unitless. One of the few things in physics where you don't have any units. For most of the things you'll be calculating in this course, definitely want to remember those units, because on the free response you will definitely be losing points for not including correct units. Unless, of course, the problem is, one of those like expression problems where you don't actually have to solve for numbers in the end. But if you do actually have to solve for a number, remember to include the units. Start developing that habit early. I would hope you already started doing that with me. I'm pretty sure I made sure to include units on every answer that I've given, wherever the answer was numerical at least, up to this point. I would hope after teaching this stuff for 10 plus years that I've developed a pretty strong habit of including my units, or at least very quickly catching whenever I'm forgetting them. Anyway, where do we want to go from here? Let me see what else we have. So I guess I wanted to talk about Oh, actually, let me look this up before I forget about it. Let me find, there's got to be table of friction coefficients. Ah, here we go, the engineering toolbox. I think this was the right website. Oh, and this is reminding me of something else. Okay, yeah, I'm glad I did this. Okay. So let me switch screens here. Okay, so this is from a website called engineeringtoolbox.com. It's got a bunch of friction coefficients versus materials and surface conditions. So surface conditions, it depends on whether, the surface is clean and dry, lubricated and greasy, wet, dry, all that stuff. All of that can change the friction coefficients. Over here you've got whatever the static friction coefficients are. Sometimes they are, as you can see, variable. Here's your kinetic friction coefficients, which are also sometimes called sliding friction coefficients. So if you see the term sliding friction, it's talking about kinetic friction there. And yeah, you've got aluminum on aluminum under clean and dry conditions, gives you a static friction coefficient of somewhere between 1.05 and 1.35, and a kinetic friction coefficient of 0.4. And you can just keep going down the list and seeing different combinations of material. Brass against steel, you've got 0.51 and 0.44. I wanted to scroll down to, there had to be one where I'm looking for something where, well, I guess glass on glass. Here's something that you might not easily expect. Glass on glass, you typically think of glass as being really smooth, but in fact, glass has one of the highest friction coefficients, especially against another piece of glass. Where was, I know there was one here, unless I'm thinking of the wrong chart. I know they had one here where the coefficient of friction was, yeah, here we go, platinum on platinum. Coefficient of friction is 1.2. So there is a common misconception, and I fell victim to this misconception too back in the day, unfortunately, but I learned there is this misconception that friction coefficients are always fractions less than 1. That's not true. Friction coefficients can exceed 1. Wasn't there? I'm pretty sure I remember there was one here. Here's another. Rubber on rubber is 1.16. Here's silver on silver is 1.4. And if I remember correctly, there was one that was like 2 point something. Unless I'm thinking of a different chart. Yeah, that's the end of it, so I guess I'm thinking of a different table. But there are combinations of materials that can give you some really high friction coefficients. I might be misremembering, but I think the highest I ever saw was greater than 4. But most of the time, as you can see in the majority of this chart, your friction coefficients are going to be somewhere between 0 and 1. So if you calculate a friction coefficient and it's greater than 1, it doesn't automatically mean that it's wrong, but do double check your work, because 99% of the time that's not supposed to happen. Be careful about friction coefficients that are calculated too high. It's not impossible, but chances are, if you calculated a friction coefficient greater than 1, then there might be something wrong with your work. Okay, that takes care of that. Now I want to do, let me think here. What do I want to do next? I guess we can either do, let me see, any of these two-dimensional, well, I guess it's time to talk about Newton's third law. So I already have a video going over Newton's third law. I already have a video going over that, which you can find, where is it? I think it's video number 6 under the misconceptions section of the videos and resources. So yeah, if you go to the course plan, again, linked in the description. I know some of you are tired of me saying that, but some people might be new here and hearing it for the first time. If you're looking for this page, it's linked in the description. If you scroll down to Unit 3 Force and open up the tab for it, under Addressing Misconceptions, I'm pretty sure it's number 6. It's one of these. I'm pretty sure it's the last one. I do go over Newton's third law in some depth there, and I think I'm pretty much going to do right here most of what's in that video. So let's go over Newton's third law and still watch that video later, even if I end up covering everything that's supposed to be in that video here right now. It bears repeating. It's definitely a good idea to listen to the explanation again. So Newton's third law. Newton's third law. Newton's first law was called the law of inertia, and Newton's second law was called the law of acceleration. Newton's third law, you can probably guess, is called the law of reaction. And we all know what it says. For every action, there is an equal and opposite reaction. For every action, there is an equal and opposite reaction. There is an equal and opposite, reaction. That is not a very legible O, but you know what it's supposed to say. Okay, well, equal in what way and opposite in what way? Well, the opposite part is easy. Opposite in direction. Equal has more to it than just equality in magnitude. Action and reaction are a pair of forces that are equal to each other in magnitude, but that's not the only thing that's equal about them. So here's something that's commonly misunderstood about Newton's third law. Here's something that's commonly misunderstood. Action and reaction are not only equal in magnitude. Action and reaction must be equal in nature, must be of an equal nature. That is to say, that's just a fancy way of saying they must be the same type of force, must be of an equal nature or character or whatever you want to substitute this word with. Translation, must be same type of force. Must be same type of force. Guess what I'm about to rant about again? Oh yeah, you guessed it. Normal force being equal to mg. The force of gravity is equal to mg. The normal force is not necessarily equal to mg, and even when it is, it's not because it has any direct relationship with the force of gravity. Over here, if this object is at rest, its acceleration is 0 in the vertical direction, then yeah, the normal force has to be equal to mg because the net force has to be 0. The force up has to cancel with the force down. That doesn't mean that normal force has the formula mg, and some teachers will give this formula to their students and justify it by saying, oh, well, the normal force is mg because it's a reaction to the gravitational force. Wrong! Wrong! Normal force is not a reaction to gravitational force. The reaction to a normal force must be another normal force, and the reaction to a gravitational force must be another gravitational force. But wait a minute, then where is the reaction to this normal force, and where is the reaction to this gravitational force? Well, the reaction to this normal force is easy enough to show. The reaction to the normal force that the ground exerts on this box is the normal force that the box exerts back on the ground. And the reaction to the gravitational force that the Earth exerts on the box is the gravitational force that the box exerts on the Earth. And we'll call this Earth's core. We'll call this Earth's core, or to be more precise, Earth's center of mass, which might not be exactly in the middle of its core, but close enough. Earth's center of mass. That's where the gravitational force is, and that's why we don't draw it. Do you really want to have to draw the entire planet every time you want to draw a box on the ground? Maybe if we wanted to calculate how the planet moves, but usually that's not the problem that we're dealing with. And when it is, we're usually looking at a much bigger picture anyway. We're looking at something like between the Earth and a satellite, and we can draw a really zoomed out picture in that case. So that's where the reaction to the gravitational force on the box is. It's on the Earth's center of mass. It's there, but we usually don't draw it because we're usually concerned with one object. So that's one of the important things to remember about action and reaction. They're not only equal in magnitude, they also have to be of an equal nature. This also tells us another thing, that just because two forces are equal in magnitude, like this gravitational force and this normal force are, just because they're equal in magnitude doesn't mean they have some sort of action-reaction relationship between them. So equality of magnitude with opposite directions does not imply that two forces are an action-reaction pair. This is the last thing I mentioned in that video, actually. So I'm bringing it up earlier here. Equality of magnitude with opposite directions does not imply that two forces are an action-reaction pair. It only goes one way. If you identify two things as being action and reaction, then they must be opposite in direction and equal in magnitude. But if you go the other way around, if you find two forces that are equal in magnitude and opposite in direction, the logic doesn't work in reverse. That does not imply that the two forces are related in this action-reaction relationship. So that's another thing that must be noted. A third thing that helps dispel this misconception of normal force being a reaction to the gravitational force. Another reason why this is impossible is because this normal force and this gravitational force act on the same object. And for action and reaction, that cannot be true. Action and reaction always act on two separate objects. Always act on two separate objects. If I were to write Newton's third law in the form of an equation, basically the force of object 1 on object 2 would be equal to the negative of the force of object 2 on object 1. You need two objects for this to be possible, and the negative sign just means opposite in direction. That's why I'm including the arrowheads for once. to remind you that force is a vector and that the negative sign means a reversal of direction here. Action and reaction always act on two separate objects. That is why action and reaction can never cancel each other out. For forces to cancel out with one another, they have to act on the same object. This gravitational force can only cancel this normal force because they act on the same object. This gravitational force that the Earth exerts on the box can never cancel with the gravitational force that the box exerts back on the Earth, because they're not the same object. Now, if you were to treat the box and the Earth as just being one combined object whose total mass is the mass of the Earth plus the mass of this box, then that internal force would disappear. Kind of like what we did in the beginning over here, where we took the block and the elevator, and we treated them as a single 340 kilogram object, and then the two tension forces over here disappeared. That's because they were an action and reaction pair, and we saw mathematically how they cancel out when we combine the two masses together. At that point, these two forces would need to disappear because an action and reaction cannot exist all on a single object. You would actually have to cut this object up into parts in order to draw a pair of forces on it. You would have to cut it into at least two parts, which is what it was originally before we combined it. So that's a little bit more insight on what we did there. I didn't really plan for that, but now I'm glad that I did that. Let me see, anything else I want to mention? I mean, you're going to get everything from that video I mentioned, which you should definitely watch. But is there anything super important that I want to bring up now before you go watch that? Let's see, action and reaction must be of an equal nature, equality of magnitude with opposite directions does not imply that two forces are an action-reaction pair, and action and reaction always act on two separate objects. Okay, so here's another one, which is about language. This one's about language. So, action and reaction come into existence. And disappear from existence, and disappear simultaneously. If I push down on the table, it pushes up on my hand. If I push down harder, the table pushes up harder. You can feel this as you go. If you push, maybe not on a table, but on a wall, same thing happens. The harder you push against it, the harder the push you feel back against you. When you increase the force that you apply, the force that the table or wall applies on you also increases at the same time. It is happening at the same time. It's happening simultaneously. There is no delay. The words action and reaction can be a little bit misleading only because of our colloquial definitions of the words action and reaction, specifically reaction. We usually think of the word reaction as something that happens after. Colloquially, I don't know if I'm spelling this right. I think I am. Colloquially, reaction is thought of as something that happens after, is thought of as something that happens after. But that's not true in physics. As something that happens after. But this is not true in physics. The definition of the word reaction in physics, it just means something different. And if that idea is foreign to you, then think about another context where the word reaction has a different meaning. What about in chemistry? A reaction in chemistry definitely does not mean what it usually means in everyday life. It doesn't mean a response per se, right? It implies something quite different from the usual way we use the word reaction. Well, it's the same thing in physics. The word reaction just has a different meaning in physics. When we say something is a reaction in physics, we are saying that there's some sort of relationship between it and some other force. In fact, because action and reaction always come into existence simultaneously and disappear simultaneously, and increase and decrease simultaneously, there is no way to indicate which one came first, because they both came first. They both come in at the same time. They both disappear at the same time. Whenever one is removed, the other is removed. Whenever one comes into existence, the other comes into existence. There's no delay. There is no first one. So actually, it doesn't matter if I go back to this diagram. If I pick, for example, these two forces, the normal force of the ground on the box and the normal force of the box on the ground, I can say this is the action and this is the reaction, but it's also fair to say that this is the action and this is the reaction. There is no priority. Both of these have some sort of relationship between them where they must be equal and opposite, and that's what ultimately matters. It doesn't matter which one you call the action and which one you call the reaction. It's a completely arbitrary choice. So don't get too hung up on that. Reaction is just a relative concept. They're both a reaction to each other, and they are both actions for each other. So yeah, English is important is, I guess, what I'm trying to say here. I know I frequently joke about how I'm not the English tutor, but part of doing well in science is learning how to speak the language of science. And the language of science, it might be unappealing to you because it sounds all nerdy and esoteric, and it feels like we use all of these complicated sounding words just to be confusing on purpose. It's not to be confusing on purpose. It's for the sake of communicating clearly. In order to do science, you need to have an agreement with other scientists on how you are going to communicate ideas. So, language matters. The sad reality is, though, you read some scientific papers and you realize that even the people that are publishing a bunch of papers, you'll spot grammatical errors and poorly worded paragraphs or sentences, and I guess that's all the more reason why you should care. Language is a big deal. I'm not saying you have to memorize the entire dictionary, but, just get into the habit of, if you encounter a word, just quickly Google it instead of glossing over it and, hand-waving it. Just Google it and see what it means, and then continue reading your article or social media post or whatever it is you happened to be reading when you found the word. And if you never encounter the word again, then of course you're going to forget it. But if you do end up encountering the word again, you might have to look it up again, and then you encounter it a third time a few weeks later. And if you encounter it enough times, well, that obviously means it's a word worth knowing. And if you just look it up every time you run into it, eventually you won't have to look it up anymore. You'll just learn what it is. That's how you build up your vocabulary. But if you're just looking for a vocab list, then it wouldn't hurt to just go through, your textbook's glossary and start looking at terms you want to prioritize from there. But yeah, I guess your word of the day is reaction in the context of physics. So there you go. I gave you your head start. Oh, and I see we have a question in the chat. It says message retracted. Okay, I don't know what that's about, but I guess I'll have to look through the history and see what happened there. I wish it would also tell me the time that the message came in. There probably is a way to do that. But yeah, if you still have a question and you want to try posting it again, I don't know if YouTube automatically filtered it for some stupid reason. But yeah, feel free to ask questions and do be patient with me. Sometimes it takes me a bit to notice when there's activity in the chat. Usually no more than 5 minutes. Anyway, how are we doing on time? We've been going for about 2 hours, so yeah, I think we can keep going for a little more. Is there anything else I want to say here about Newton's third law? Oh, of course, the important one. One of the big points of confusion for a lot of people. Newton's third law is about force. Equal and opposite force does not imply equal and opposite motion, does not imply equal and opposite motion. Okay, what do we mean by this? Well, some people will ask if, say a soccer player. I think this is always my go-to example for this. If a soccer player kicks a soccer ball, they are in contact for a certain amount of time, and there's going to be some force that the player exerts on the soccer ball, and there should be an equal amount of force that the soccer ball exerts on the player. So why is it that the player doesn't really get sent flying backwards while the soccer ball gets sent flying forward? What's going on? Well, 2 things. First thing, if these forces are equal, the masses are not equal. The mass of this soccer player is significantly greater than the mass of this soccer ball. So even for the same amount of force, if I do net force on ball equals mass of the ball times acceleration of the ball equals the net force on the player, which is equal to the mass of the player times the acceleration of the player. I'll just write P for short. Since the mass of the player is larger, for the same amount of force, their acceleration better be smaller. But that's not the only problem. The other problem is it's the net force on the player that determines the acceleration of the player. So this is already wrong. I'm assuming that the net forces on both of them are equal. Even if they were equal, their accelerations are different, but it gets worse than that because they are not equal. The net force on the player does not equal the net force on the ball. The ball is going to lift off of the ground, so it won't be subject to friction with the ground anymore, while the player will experience friction from the ground. I guess I'll do that in a different color. So here's going to be some friction from the ground. Which type? If the player doesn't slide back, it would have to be static friction. And if the player does slide back a little, it'll be kinetic friction and maybe some air resistance. And of course you have to factor, well, gravity and normal force are just going to cancel each other out for the player in this scenario, so that's not really going to make that much of a difference. It'll just allow you to calculate the normal force, which lets you calculate what the friction force could be. So yeah, you have to take other forces into consideration. It's not just the force between the player and the ball. The player also has forces between them and the ground and the air, if you want air resistance to factor in, and the earth itself. That's where the gravity comes in. So yeah, it's the net force that determines motion. It's Newton's first and second laws at work there. And that explains that little conundrum. So now what are we left with? I guess I've pretty much hit all the points in that video except for 2 of them, I think. But at least we've hit all the important ones. So there you go. We have now covered all 3 of Newton's laws. Let's go ahead and see what we can do with that. Now that we've properly discussed action and reaction, let's see if we can get through these problem sets before calling it a day. I want to do this, and, well, I might leave this one as homework. And then I definitely want to at least do one of these. Okay, let's get started. So let me see, anything in the reminder that I want to emphasize? It says in 2-dimensional problems, it's best to think of the vertical part of a problem separately. Yeah, we already talked about that. Okay, and so scenario 1, we've got a student drags a box full of textbooks by a rope as shown. So we've got a 40-kilogram box. We've got a rope. It says the tension force in the rope is 35 newtons, and the student pulls at an angle of 20 degrees above the horizontal direction. What is the normal force on the box, and what is the acceleration of the box? Okay, that shouldn't be too hard. So 2-dimensional force problems, here we go. We have our object. We've got a force of tension on it. Force of tension equals, it said 35 newtons at a 20-degree angle, 20 degrees. And it was a 40-kilogram box. 40-kilogram box. What other forces are acting on this thing? There would have to be a force of gravity is equal to mg, and there would have to be a normal force, which we need to calculate. It's going to be less than mg, I can already tell, because there's an upward component to this tension force. So the normal force, if it was equal to mg, then the upward part of the tension force would be enough to make this box of books accelerate up into the air, which is not something you would expect for a scenario like this. They're just dragging the box along the ground. So the normal force would have to be lower in order for the net vertical force to be 0. So anything else that was given to us? Nope, and I did not draw any tick marks on this, which tells you that there's no friction. Again, if you don't remember what I said about the tick marks last week, when I draw tick marks on my surfaces, I'm implying that the surface is rough and that there is friction, and when it's not drawn, I'm implying that the surface is smooth. When the AP exam draws tick marks, it could mean either or. They're not very consistent about that. I will probably have to give that reminder every time I do one of these force problems, just in case. Because I do have people who, I can tell, I've looked at the view counts, I can tell some of you have mostly been interested in the most recent topics I've covered, projectiles and force. Not a lot of people looking at the stuff that I covered for kinematics. But maybe those will get more attention towards the end of the semester or the last month before AP exams during review time. Anyway, force of tension, 35 newtons. I want to break this into components. I want to break it into a horizontal component and a vertical component. And I would actually have to draw a separate diagram for this. So actually let me scribble these out and redraw the diagram. Let's get into that habit. I don't know how often I'm going to do this for you. I'm probably just going to draw over a single diagram a lot of the time to save space. But on the AP exam, definitely, if you want to draw components of your forces, especially for a problem that asks for a diagram as a response to a question, you definitely want to draw a separate diagram with components if you like having components on your diagrams, which I do. But a lot of times they want you to just draw the raw forces with without breaking them down into components. So anyway, force of tension is 35 times cosine of 20 degrees. Cosine will give me the adjacent component. The adjacent to the 20-degree angle is the horizontal side this time. And that's 32.889. I'll round that to 32.89 newtons. And the upward component would then have to be 35 times sine of 20 degrees. And am I in degree mode? Yes, I am. Gotta make sure you check for that. And that's giving me, if I round it, 11.97 newtons. You can call these force of tension X and force of tension Y if you want. Force of tension X and force of tension Y if you want to give names to them. Sometimes it'll be important to do that, other times it's not entirely necessary. And then you've got whatever normal force you've got. And you've got mg. I'm going to use 9.8 for g here. So 40 times 9.8 would be 392, I believe. Yep. Can you tell that I have done these physics problems way too many times? Now I know my 9.8 times tables. How sad is that? 392 newtons. Okay, so the questions were, what is the normal force on the box and what is the acceleration of the box? So for normal force, I can do net force in the y direction is equal to the mass, 40 kilograms, times the acceleration in the y direction. Well, I don't expect this box to accelerate vertically. Common sense would suggest the acceleration in the y direction here is 0. So that gives me normal force upward, plus I also have this 11.97 upward, minus 392 downward is equal to 0. So add 392 over to 0 and subtract 11.97. 392 minus 11.97 is 380.03. So normal force is equal to 380.03 newtons. Not quite equal to the force of gravity. In fact, if I really wanted to draw this to scale, I would redraw the normal force almost as long as the gravitational force, and I would draw this force of tension y really, really tiny. But again, I did not know in advance what the normal force would be or what the scale would be. Well, I guess I should have known because of this 11.97 compared to 392. I should have known at least that this would have to be much smaller than this. But that's part A, so I'll go ahead and circle that. And then part B was asking, what is the acceleration of the box? Okay, well, we know there's no acceleration vertically, so all the acceleration must be horizontal. What is the acceleration of the box? Acceleration of the box is equal to the square root of its horizontal acceleration squared plus its vertical acceleration squared. This is how you would do it if there was both a horizontal and a vertical, but since the vertical is 0, this is just the square root of the horizontal squared, which is just equal to the horizontal. If the only acceleration is in the horizontal direction, then the overall acceleration is just that horizontal part. Same as with the elevator problem if all the acceleration was in the vertical direction. But do remember this because you might run into scenarios where you have some sort of two-dimensional acceleration to calculate. It'll probably be rare. We might see some of it in a later chapter when we talk about not just circular motion, but also what's it called? Rotational kinematics. When we combine those two, there will be a couple of scenarios where we might want to do this. Otherwise, we're not going to encounter this very frequently, if at all, in the current chapter. It's not impossible, but it's rare. I could dig around for a problem where we have to do this, but just know that it is an option. All of the rules for finding the magnitudes of two-dimensional vectors that we learned in the past still apply. It's still just the square root of the sum of the squares of the components if you actually have two non-zero components. Anyway, acceleration in x can be calculated from net force in x. So let me grab another color here. How about you? So net force in the x direction is equal to the mass, 40 kilograms, times the acceleration in the x direction, which I don't know, that's what I'm solving for, is equal to forces in the horizontal direction are 32.89, and that's it. All I have is 32.89 to the right, and nothing to add or subtract. So 32.89 divided by 40 looks like an acceleration of about, what, 0.8 and some change? 32.89 divided by 40, 0.82225. I'm just going to round it to 0.822. Acceleration in the x direction is 0.822 meters per second squared. And I guess we can now ask a follow-up question. Actually, I should have brought this up last week. I don't know what I was thinking. Newton's second law, net force equals mass times acceleration. This is your bridge between force problems and kinematics problems. You can either use force to figure out the acceleration, which you can then use to solve some sort of kinematics problem, or you can do kinematics and figure out acceleration, which you can then plug into net force equals ma to figure something out about force. You can have problems that go in either direction, and we'll see some of that eventually as time goes on. I could ask right now, bonus question, it's not really stated here. I could ask, for example, how far does this box full of textbooks travel in 5 seconds, assuming that it started from rest? We can do that now. We can do that. How far? So bonus question. How far how far, I'm going to restart that, how far does the box move in 5 seconds if it starts from rest. And this, of course, is assuming that this tension force is maintained while it's moving, which is kind of difficult to do because, you know, if you pull on something, it moves and then the angle of your rope will change. And also, if you don't, you know, move backward at a good enough pace while dragging a box, then the box catches up to you and the rope slackens. Again, what I showed earlier today, right? If you're pulling on something and you successfully drag it over and then you don't move back as quickly as it's moving towards you, then you get this happening. So easier said than done, but assuming that the force is maintained, assuming that this magnitude and this angle of force are by some miracle maintained for 5 seconds so that the acceleration doesn't change, how far does the box move in 5 seconds if it starts from rest? Well, we are told by the starts from rest that v initial is 0, and we just got the, well, we don't need to know v final, but listing it anyway. Acceleration, at least in the x direction, is 0.822 meters per second squared. Time is 5 seconds, and displacement in the horizontal is currently unknown. We can calculate both of our unknowns. We've got 3 of our kinematic variables, and that's always enough to calculate the other 2. So I'm gonna do which equation? I guess second equation is all we need here. Delta x is equal to v initial times t, so 0, plus 1/2 a in the x direction, t squared. So delta x is equal to, that's a 0, so that's gone, 1/2 times 0.822 times 5 squared. Okay, 25 times 0.411. 0.411 times 25 is 10.275. 10.275 meters. And there you go. So yeah, you absolutely do still have to remember your kinematics for this chapter. You don't get to just forget about that. It will come into play from time to time. Oh boy, will it come into play. We are going to have some problems that definitely require you to tap into your kinematics skills. So hopefully you haven't forgotten all that, but if you have, you are in luck because you have at least a week, maybe more depending on when I get to those problems, to review. Okay, so now that we're done with that, let's take a look at one that involves friction. A worker is trying to push a box as shown. If the worker applies 40 newtons of force at an angle of 30 degrees below the horizontal and the coefficient of kinetic friction is 0.15, what will be the acceleration of the box? Okay. What color do I want to use? Let's use this one. Didn't mean to draw through that. Oh well, you can always rewind to see what it used to say. Okay, so diagram. We've got a rough floor. I'm just going to draw the box. I'm not going to draw the person pushing on it. And it said that they apply 40 newtons of force at 30 degrees below horizontal. So I'm going to draw a horizontal reference line and then 30 degrees below that. I hope I drew that well enough. So this is supposed to be 30 degrees, and this is supposed to be a 40 newton, I guess we'll call it force applied. You can also call it a normal force because technically they would be just pushing it against their hand. What else is in this diagram? So, of course, this is presumably on Earth, so force of gravity. This was a 15 kilogram object. Now, you don't need to write the mass of the object on your diagram, but I like to do it. It doesn't hurt. There's going to be a normal force, which I know at the very least is going to be greater than the gravitational force, but I didn't have enough room, otherwise I would have made it longer. And there's going to be, well, it says the worker is trying to push a box, but it also only gives the coefficient of kinetic friction, which implies that the static friction loses out. Otherwise, the static friction would have been mentioned. Actually, you know what I'm going to do? I'm going to ask a bonus question. What should the coefficient of static friction be at a minimum in order to prevent motion? That will be my bonus question. But for now, kinetic friction. In the absence of friction, which way would this box move? Looking at all these other forces I drew, it looks like the vertical forces are going to cancel out, and all that's going to be left is one horizontal force to the right. So without friction, this object would have moved to the right, assuming that it started at rest. So the kinetic friction then would have to be to the left. Force of friction, kinetic, would have to be to the left, and it is assumed that this object will start moving to the right. Okay, so coefficient of kinetic friction was given to us as 0.15, so mu k. Sometimes I just draw this somewhere on the rough surface in my diagram. Mu k equals 0.15. And I guess we've got some work to do. So force applied is going to have two components. One that points downward, one that points downward. I guess we can call that force applied y. And a component that points rightward. I'll call that force applied x. And if I try to net my forces in the x and y directions, let's see what happens. So net forces, I think I want to do the y direction first because I need it to figure out the x's. I need to net my forces in the y to figure out what my normal force is, and I need to know my normal force to calculate what my friction force is. So net force in the y direction is equal to mass 15 kilograms times acceleration in the y direction, which we can reasonably assume is 0. I have no reason to assume that this object is going to accelerate up into the air or down into the ground. Equals forces up minus forces down is how I like to do it, but you can also do down minus up. At the end of the day, 0 up is the same as 0 down, so it's not really going to matter. Normal force upward minus downward, we've got mg, and we also have force applied y. So those are both going to be subtracted. And then let's see, so 0 equals the normal force minus mg. 15 times 9.8 is 147. And I know that because I've been teaching physics for too long. Minus force applied y. That's going to be 40 times, is it sine or cosine? Well, the 30 degrees is touching the horizontal part. So the cosine is going to go with the horizontal, which means the sine is going to go with the vertical. 40 sine of 30. Sine of 30 is 1/2. So 40 times 1/2 is 20. Okay, and that leaves us with a normal force of add 147 and add 20 over to the 0 side. That would be 167. Normal force is equal to 167 newtons. Okay, and from there, I want to do net force in the x direction. Net force in the x direction for this object is going to be, I'm going to do right minus left. So it's going to be 15 kilograms times acceleration in the x direction, which we do not know yet, is equal to forces to the right. So that's going to be force applied x minus forces to the left, force of friction, kinetic, whatever it is. So that's going to be 15 acceleration in x equals force applied x, 40 times, we already did sine, so the other component must be cosine. 40 cosine of 30 degrees is 34.64 minus the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force is equal to 34.64 minus 0.15 times normal force was 167. Okay, so that'll be 0.15 times 167 equals 25.05. 34.64 minus 25.05 is 15 acceleration in x. Okay. 34.64 minus 25.05 is 9.59. And if I divide that by 15, 9.59 divided by 15 is 0.639 and then a bunch of threes. So I guess I'll write 9.59 equals 15a. And then divide by 15, acceleration in the x direction is 0.639. And then a bunch of repeating threes. I'll just round it to 0.639 meters per second squared. So that is the main question all done. We got the normal force, we got the acceleration. Oh, and I forgot to circle this answer back for the previous problem. Anyway, so next up I want to do, how about we do green? I see my chair is complaining. Maybe it's time to buy a new one. I mean, it doesn't look like there's anything wrong with it. It still feels sturdy enough. Let me see. Lost my train of thought. Oh, right. Bonus question. So my bonus question is, what minimum coefficient of static friction is needed to prevent this box from moving? From moving. That's going to be my bonus question. What coefficient of static friction, implication coefficient of maximum static friction, what maximum coefficient of static friction is needed to prevent this box from moving? So what we can do, I guess one way to look at this, I think the better way to do this, and it's not the way that most teachers teach you to do this, is to just do it in the inequality form. So I want the static friction to be such that what? Well, the floor is stationary, so to be under static friction, the box must also be stationary, must move at the same velocity as the floor. So I want the box to be stationary, which means I need the acceleration horizontal to be 0. So what I want to do is rewrite my net force x equation and set my acceleration to 0. Under those circumstances, net force x equals 15 times 0 is equal to, that's still 34.64 for the horizontal part of the applied force, minus force of friction static, and I want it to be maxed out. I would want it to be maxed out. Well, I'll leave max out of it for now, just in case it's not intuitive why it would have to be max. I think it'll make more sense once we get to the inequality formula for, or not formula, what would we call it? The inequality expression for static friction. So I want my force of static friction to, well, if I add it to both sides, there's a 0 here now. So force of static friction, I want my force of friction static to be equal to 34.64. Okay, then that means I want 34.64. I want 34.64 to be less than or equal to some coefficient of static friction times the normal force. I want 34.64 to be less than or equal to the maximum coefficient of static friction times the normal force, which was 167. So whatever this number is, of course, I could make it, for example, 1 times 167 satisfies this inequality. 167 is definitely greater than 34.64, so I could go with 1 and call it a day, but that's not really precise. That's kind of cheesing your way to an answer. It's a very trivial solution. It's not much of a challenge or a question, so you wouldn't expect it to be that easy on the AP exam. I could do half of that. I could do 0.5 if I had a coefficient of static friction of 0.5. 0.5 times 167 is going to be what? 83.5, which is still greater than 34.64. So it would work with a coefficient of a half. And I can still afford to go even lower. So the question is, what is the lowest I can go? That's why the question is, what is the minimum? Because the maximum, you can go as high as the sky, or at least as high as the roughest material known to man will allow you to go, which, again, I don't remember, but I think it was like 4 point something. I could be wrong on that. But at least in the chart that we saw earlier, what was the highest number we saw? Like 1.2? And I know there's higher than that. So yeah, if we were looking for the maximum, the sky is the limit. You can you can go as high as you want within reason. It wouldn't really be a challenge. The real challenge is figuring out what's the minimum static friction needed. And as a bonus, I guess we could go back to that website and pick out a material that would be the best material for the situation. That might be an interesting thing to do. So of course, I'm just going to divide by 167. 34.64 over 167 is equal to 0.207. Is equal to 0.207. And is that still visible on the screen? Yes, it is. 0.207 is less than or equal to the coefficient of static friction maximum. So yeah, I want my maximum static friction coefficient to be greater than or equal to 0.207, which means 0.207 is the least it can be. 0.207 is the minimum. 0.207 is the minimum coefficient of static friction necessary to prevent this object from moving. Okay, how are we doing on time? Do we have time to do more? Well, I would have liked to... I don't know. Maybe we should save it for next time. Yeah, I'll talk about this problem real quick, and I guess we will save this for next time. I guess I'll talk about it a little bit. So over here we've got... Oh, wait, you didn't see that on the screen. Great, now I'm having the reverse of the problem of last week. So what I was saying is, I want to go over this and maybe talk about this a little bit. So I don't want to do this problem, but I just want to give some pointers. So it says 2 pirates are trying to salvage some treasure from the ocean. They get the treasure onto a wooden plank with cables and pull on the cables. The pirate shown in red creates 800 newtons of tension in his cable. That's this guy right here. He's pulling with a force of 800 newtons, and the angle is 78 degrees above the horizontal. You can see why I couldn't really squeeze it into the drawing there. The pirate shown in orange, this guy on the right, pulls on his cable at a 63 degree angle. The plank doesn't wobble. Its motion is completely vertical. That is an important hint. Motion completely vertical means what for the horizontal? That's something I will leave for you to figure out, although I guess you could also look at the answer key video if you get stuck. I do have an answer key for this one, don't I? Let me check. Yeah, I should have answer keys for all of these from this point on. Okay, so yeah, if you get stuck, I mean, try it on your own first, obviously. Don't just rush to the solutions. And then the reminder is, remember that the plank and the treasure move together, so they should each have the same acceleration. That's another important hint. This plank and treasure are basically an upside down version of what we saw at the beginning today with the elevator and the hanging block connected to its ceiling by a rope. So that is something to consider. You might find some similarity between those. And since you've got 2 objects, you're going to draw 2 diagrams, and there's at least one force in common between both of these objects. Figure out what that force is, and remember what we learned today about Newton's third law. I guess that kind of gives it away a little bit. And if all else fails, you do have the solution in a video. Okay, as for this one, it's also solved in a video, but I'll probably just go over it at the beginning next time anyway. I mean, it doesn't hurt to preview it. So you don't have to do the warm-up if you're already good at solving equations by elimination, but the reason I include that here is because these problems where you have multiple objects connected by ropes usually lend themselves to elimination. You will usually end up writing equations for each object where you can put the equations together in such a way that some of your variables get canceled out through elimination. So if you want to go ahead and try that, you can. Essentially, what you have is, so we already did situations where you have two objects requiring two force diagrams. Now you have three objects requiring three force diagrams, and for each rope you're going to have, I would assume, different tensions. Different ropes, I would expect different tensions in them. So this rope over here on the right, it will have some sort of tension with which it pulls the 8 kilogram block to the left and pulls the 3 kilogram block with an equal force to the right. And then this one pulls left on the 3 and right on the 5 with, I would assume, a different tension force. It'll be quite the coincidence if these two tension forces are the same. They better not be, because I didn't write this problem for them to be the same. But yeah, I think that's all I wanted to say on that. And again, we will do this next time. This is where I intend to start, unless I think about it over the week and change my mind and decide on some different approach. Yeah, another class of problems is what awaits us next time. So I think that is where I will wrap things up. Is there anything else here I wanted to say? I think I'm good. Let's see, that was 15. 16 is systems of objects. What do I have in the friction thing? I'm guessing it's just the same as... Oh, wait, no. That's not... Wait. What's this? Oh. How did I skip this? Okay, yeah, this also looks like it's going to be part of what we do next time. So we're going to do systems of objects, which is just what you do when you have situations with multiple objects. I kind of already showed it here today with that elevator problem especially. You can write equations where some of your variables will get eliminated, and you'll find a pattern where you'll be able to treat a collection of objects as just a single object whose mass is equal to the sum of the masses of the individual parts. And you can come up with some useful shortcuts there. Don't become over-reliant on those shortcuts. I would still want you to learn how to do things, the traditional way, because sometimes those shortcuts will fail you. If you remember what I said about shortcuts back when did I say it? When we first started deriving some of the shortcuts for symmetric cases for free fall. If you are going to use them, you need to be able to prove them. You need to be able to understand how to do things from base principles first before relying on your shortcuts. And if anything, rely on shortcuts only for when you're under a strict time limit, and having an answer is better than having no answer at all, or use them as just a quick way to kind of check your work and figure out, if you're on the right track. Just use it as a way to check, does the answer I got meet my expectations according to the shortcut I know? Or is something incredibly wrong? But yeah, that'll be next time. We'll look at systems of objects, and we will also do the same thing but add friction to the mix. And if we have time, we will probably also be able to squeeze in the topic of inclined planes. And then the time after that, I'm pretty sure, is when we will have to wait in order to combine inclined planes with friction, with ropes. And then I imagine it'll be the week after that. No, wait, let me think here. Hold on. So next week we will do this, and probably this. We will do those three, most likely. And then the week after that, we will do this. Yeah, we'll combine what we learned from here all into one type of problem here, and then we will add pulleys to the mix, and then we will combine all of this into one big complicated type of problem, which isn't actually super complicated. You're going to see worse than what you see over here, but that's kind of how I've organized it, as just one piece of this type of problem at a time, dealing with each kind of twist separately and then putting it all together in the end. Okay. Any other announcements? I am not doing traditional office hours this evening. I'm actually not sure when I will do them. Maybe tomorrow, or maybe the day after. I'm not entirely sure. And there might be an extra surprise stream over Thanksgiving break if I find the free time, just so that we can, get a move on a little bit faster, but that's not a promise. So for now, the going assumption is that we'll just continue on Sunday, but if I can sneak in an extra session, then I will try and go for that. Although, honestly, I'm behind on some other stuff, so that is not very likely to happen, but it's not impossible. And I think now I am done with announcements. So, yeah, take care, study hard, have a good Thanksgiving break if I don't see you then. And what else? Don't forget to do your homework. And I think that's it. Class dismissed.